Alright, so we're going to continue with these slides about objects and classes. So we start with structs, right? That was just a way to make your own type that had little types inside of it. Struct point, struct line segment, whatever that was. Cool. That could have a point inside of it. You can just build on top of your things. So you're making types with things inside. And then classes were structs plus operations, right? Data plus operations. So you could have things called methods attached to your objects. You have little messages that you can send your things. So the point class now has space for the x and y, but it also remembers how to respond to these messages, how to negate itself, how to add itself to some other point, how to scale itself. There's always a concept of your current object. There's always a concept of the self, right? So that's fun. That led us to the idea of object-oriented programming, just doing this a lot. That's what object-oriented programming is all about, okay? So, yeah, we had a nice example with points and things. What I'd like to do now is redo that example, because I did it the lazy way, okay? So I implemented all my methods inside of the point class, and that was not really correct. It's not the cool way to do it, not the standard way. So we're lecture 15. Okay. Before we go there, I'd like to copy lecture 14's classes.cpp into lecture 15. And I think I should call it something different anyway, but let's figure this out together. Let's call it point.cpp. I think that would be best. Let me confirm that that is a good idea. Yeah, point.cpp. Okay, so now it's called point.cpp. Let's look at it. So here's my class. Point, double x, double y, negate. I gave the method and I implemented it right inside the class. Okay, right inside the curly braces. That's the lazy way of doing things. Same with add, same with scale. These are all implemented inside of the class declaration. This whole thing inside of these curly braces is the declaration of the class. Really, you shouldn't be putting implementations there. Okay, so it'd be nice to split up the declaration of the class, just what a user needs to know how to use in order to use it, right? Just the names of the methods, the types that they have. To split that up with putting that in like a header file, and then the implementation of the class somewhere else. All the methods go and be implemented in a .cpp file, okay? You can even split things up in the same file. Maybe we'll do that first, okay? So let us, let's do that. So we are going to implement our methods outside of the class. We're going to declare the fact that they exist inside the class declaration, and we're going to implement them outside of the class, okay? So let's do that. So negate, add all this stuff, boop, 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 goodbye, go outside. So now they're all outside the class. But we also want to just, tell the class that they exist, so we'll put them up here. Be like, void negate, point add, all that stuff. We have to say that they exist before we implement them. Let's see, do that, do that. Oops. What did I do wrong? There we go. Boop, boop, boop. Alright, so you got your fields, you got your methods, and then here's the implementations of all the methods down here. But this is not quite right yet, okay? Because what does this look like? It just looks like a normal function, right? As far as C++ is concerned, it can't tell, like, you're implementing a method versus you're implementing a function. You have to specify. So this, by default, is C++ thinks it's just a negate function. It's like, what are you doing with x and y? Those don't exist, dude. So you have to tell C++ that, no, I'm implementing points negate method, which has x and y member variables. Otherwise, this just looks like a function, right? That's not good enough. So once you implement the methods outside of your class, you need to tell C++ that they belong to a class and which one, okay? So the name of the function, which is really a method, right? The name of the method, I should say, gets prefixed with the name of the class : Again, the : shows up. Remember that as apostrophe S. It's like points negate method. So the name of the method is not just negate. Otherwise, C++ thinks that's just a function. It's point : negate. That's how we mark, hey, this is a method of the point class. It's points negate function. Read the : as an apostrophe S. And then the underlines go away. It's like, okay, yes, X and Y, those are your member variables. Those exist. So we do that for everybody. Point : add. This is the add method for the point class. The name of the method involves the name of the class. That's how C++ can differentiate between like this, which just looks like a function and has no X and Y, to, oh, this is a method of the point class. I'm allowed to talk about my member variables. Okay? Any questions about that? So that's, you can declare your methods inside the class and implement them outside. You just got to remember that the name of the method needs to be qualified with the name of the class. Otherwise, it looks like a normal function, and C++ gets confused. Okay, so this will work. This will all compile and run. I don't know what I want to do. I'll call it point.cpp-o point. It'll still compile, still run, do everything like we were doing. Yay. Beautiful. All the stuff that we were doing in main. So that's the first thing, okay? Class writing skills number 1. You want to declare everything, just make a nice class definition, and then implement outside of the class all your methods. Okay? Are you good with that? Any questions about that? I think I'd like to do the splitting up now. I'd like to make a header file, an implementation file, and then a file that uses my point class, like a main file. So let's do all that. So let's make point.h. This will hold the declaration of the point class. Header file guards, and we're just going to plop this right here. Boop, boop. So it'll hold the declaration of the point class. Okay? And then point.cpp is going to, I don't even know if it needs IOStream, probably not. Yeah. Point.cpp is going to, I'll get rid of the main function in just a second. It needs to implement the point class. It has all the implementations, right? And now you know why I have you include the header file, because usually you have to do it if you're doing object-oriented programming. Right now, C++ has no clue what point is. I need to tell it that point is a class. That's by including the header. Then it's like, oh, okay, yes, it's copying and pasting the declaration of the class into this file. It's like, okay, I know what point is now. Okay? So you're forced to, this time, include the header file, if that's where the class definition was. Okay? Let's see if this was all that I wanted to show you. Yes, this is the declaration of the point class. Okay? Oops. There. And then the implementation is going to go in point.cpp. That's where we're going to put the implementation of all the methods in the point class. Okay. Declaration, implementation. And then we'll have one last file that actually uses our point class like a library. We'll have a main.cpp that has our main function. So I'll steal all this from down here, delete, and that will go here now. And of course, it doesn't know what point is. I have to include my little point library, include point.h, which tells it about the point class, but it doesn't tell it how it's implemented, right? It just has the declaration in the header file. It only has the declaration in the header file. That's all it sees. And that's all it needs to know as for from the point of view of the user. Main.cpp just needs to know that, okay, point is a class that exists. I can set its fields, they're called X and Y. I can call add on it, stuff like that. Okay? So all together now, declaration, class definition, implementation, where we're implementing all of our methods, use in a separate file that includes our library again. And then here it is using our stuff. Okay? So now to compile, I need to give all of the implementation files. And that is point.cpp, that's the implementation of the class. And then main.cpp, which has the main function that I'm actually doing stuff in. Okay? And again, exact same output, no difference. It's just cleaner now, because everything's in separate files. Are there any questions about that? It's all split up, just like we were doing for functions. All right. So now, let me show you something cool. So I just told you to memorize last lecture that you have this, public colon. Let me tell you what that means, okay? By saying public stuff, by using public in our class, we gave complete access to our methods and to our member variables. So everything after that public colon is like user accessible. So let's go back. So that means all this stuff right here, accessible to the user. Everything below the public, accessible to the user. And that's including X and Y. Okay? So that allows us to call our methods, of course. It's like the user is somebody who's making an object of your class. So down in main, we're using our class. We're making a point P. We're saying p.x equals 42. Okay? By making x public, it's accessible to the user like that. Okay? Accessible. And then p.negate, again, that was a public method. The user is allowed to call it. Okay? Everything is visible to the user outside of the class's implementation. Of course, everything to you, the implementer of the class, is visible. Public is not for that. It's for the user who's making an object and trying to do stuff with the object. Okay? One nice thing is that there is also a private colon. Okay? And the reason for it, the reason you might want to have it, is to restrict the user from doing some things that exist in the class for you, the implementer, to mess with, but we don't trust the user of the class. They maybe shouldn't be able to access our X member variable directly. Maybe only we as the implementer should be able to call negate. The user needs to do something different and less error prone. Okay? So sometimes there are pieces of your class that you don't want the user messing with. And if they're all public pieces, the user has free reign. They're allowed to touch X and Y. They're allowed to call negate, add, and scale. They're all accessible, okay, from main. So those things that you don't want the user to touch, you make them private. You put private colon, and then everything below that is only accessible to the implementer of the class, not to the user of the class, okay? And that difference will become apparent when I have an example, okay? But are there any questions about just this terminology? So this, for example, is a line that I hope to convince you is an ugly line. We don't want to have this possible in our classes. I will tell you why in just a little bit. But before we get there, let's also go back to testing. Okay, let's test our point class a little bit. Let's get everything all wrapped together. Let's build on top of all the stuff we've been learning. So let's test our point class, and let's test every method maybe. Okay? So let's remember what it means to test. So the idea is to write a unit test, right? That's a tiny little thing that tests a small portion of your program. So you write kind of like a mini program, write a little function or something that checks one very small thing, okay? That's what a unit test is all about. And to check something, right, you have a concept or you have an idea in your mind of what's supposed to have happened, right? So in your mind, you're running the program. and figuring out what the program should have done, right? Like the things that you should expect to see happen. And then you use assert true or an if statement or something like that to figure out whether what actually happened, what you got, right, matched what you expected to see happen. Okay, so like the value should have been 2, check that it was 2, something like that, right? That's always compare what you got with what you expected. All right, so let's test negate and scale, for example. So here's an example test for negate. Let's say we have a point P. It holds x and y that are currently 42 and 43. And then here's a test. Here's a test for negate. Here's how we can make one. It's like, okay, well, let's make P. Let's actually set its x to 42 and its y to 43. Oops. And then let's call P.negate. Okay, what should have happened? Well, 42 should have become negative 42, right? 43 should have become negative 43. And that's what you compare against. You check, hey, is P's x negative 42 now? Is P's y negative 43 now? If so, we passed. Otherwise, we failed. Okay? So that is a good test for a negate, for example. So let's go back here. I would very much like to steal an assert true function from some file. I don't know where it might be, though, so let's... Okay, lecture 13 has one. Count words mean. Let me steal assert true. Back to main.cpp. Beautiful. Okay, so now I have an assert true function. Let's test our negation. So I'm just going to comment on all this other stuff. This is me using the class. You can comment it. You can uncomment it if you'd like. But here's all our stuff from before. And I'm going to instead make a test. Be like, I don't know, test negate. It'll be a little function that has one test inside of it. How about that? So void test negate. We'll just call it and it'll have a test inside of it that uses assert true to confirm whether or not the thing that we expected actually happened, right? So I'll do exactly this. I'll make a point P with 42 and 43. Let's see here. Point P, P.x equals 42, P.y equals 43, and then I'm going to call negate on that point, P.negate itself, please. And now what should have happened is x and y should now be negative 42 and negative 43, yeah? So assert true, P.x better be negative 42 now, and P.y better be negative 43 now, okay? So, and then I'll just use like a string called negate or something. That was the negate test. Does that make sense to everyone why this is a test? I do something, I make a little mini program to test the negate method, and I check that the negate method did the right thing for the values that I set up ahead of time. So this better be true. This condition better be true. Better be true that P's x is 42 and its y is negative 43. Okay? And there I am calling it in main. So let's compile and run. Oops. I'm in the wrong folder right now. So let's compile and run. And yay, it passed. So it did the right thing for negate. Cool. We have some confidence that our method did the right thing now. Make enough tests and it should work out. Let's take the same idea and make a scale test. Okay? Let's make a test scale function then that tests our scale method. So again, I'm going to make a point and call scale on it, right? That's how you make a test. You have to run the thing you're trying to run. Let's call it Q this time. Let's set Q's x to, I don't know, 2.5 and 3.5. 2.5 for the x and 3.5 for the y. And then I'll call scale, and I'll scale it by 2.0. And then what should have happened to Q? I'm sorry, it's Q.scale. What should have happened to Q? Well, it's x and it's y. Again, you should never check for equality of a double, I'm going to do it anyway right now because it will work. But again, always do the kind of equality checking that I told you about, just that approximate equality. All right, so if I scale Q's x by 2, then it multiplied it by 2, right? It should be 5. This better be 5.0, and then the other one better be 7.0. Yeah, and this is a scale test. Does that make sense to everybody? So I call scale, and I run in my mind what should have happened to Q. Well, okay, its x and y should have changed in this way. This is what the value should be now. Okay, so now those pass. And I'm pretty confident that my scale method is correct now. Okay? Any questions about that? Taking the class that we made and testing it. All right. Let's see, do I want to do that yet? Either now or on the next slide. So I want to give you some more terms now that go hand in hand with object-oriented programming. They're called encapsulation and information hiding. Okay? So encapsulation is just the idea of bundling data with methods, right, that operate on that data. So you think of it in terms of like points. They don't just hold their x and y coordinate. So every point object looks something like this. Every point. If it was P, if it was Q, doesn't matter. They all look something like this, right? They have an x and a y. They have their data that are just for them, right? Different points have different data, and you can set them different ways. They hold not only those, but also you can think of them as holding the methods. Like I know how to negate myself, just my own x and y. Like the negate is inside the point in a sense. I know how to scale just myself. I know how to add myself to somebody else. Like you think of those as being part of the class. You're putting them all together. You're bundling it. That's encapsulation. Okay? So that's just making classes and using them in a normal way. That's all encapsulation is. Then another thing is information hiding. And I think it's probably time for me to show that to you. Maybe I'll do it on the next slide, actually. Information hiding is when you allow the user to only see the stuff you want them to see. Okay? They only get to see just enough to use the class in the way that you intended. The user only gets to see the public stuff. Okay? If you say private colon anywhere, if you say private colon somewhere, anything below that private colon is not usable. It's not visible to the user. They can only use the public stuff. You can hide stuff from the user. Okay? And the whole point of using information hiding, of using private, and I'll give you the example in the point class in just a second, is that say we have some method that's just for us, some private method, right? I don't know. Maybe there's a fancy method that negate calls and does something fancy, and it goes and does it in a weird way. The whole point of hiding information from the user is that you can go off and you can implement another version. You can implement the same method in a different way. You can implement a faster / better version of your class, right? And as long as the public methods that you let the user see and use, as long as those still work, nobody cares, because the class still does the exact same thing from the user's point of view, okay? You can make like 50 member variables and have them do weird things, as long as everything still works as the user can see, all the public stuff still does the same thing from the user's point of view, then you can change your class all you want. You just hide the information that is only relevant to the implementer. Okay? You hide information from the user. They only get to see just enough, and that helps you keep stuff from them and only do the stuff, or how do I want to explain this? It just gives you a finer grain of control, I guess. That's how I want to say it. It lets you tell the user exactly what they're allowed to do. They can't touch pieces of the class that you don't want them touching. All right? And this will make a lot more sense with an example, I promise. We're getting there. So the next thing that I want to say is just want to point out, I did say this last time, string and vector, those are classes. You've already interacted with classes. String s equals blah. A string is a class. You just made an object of the string type. s.at2, you called the method. You called the at method on strings, on s. Cool. A vector, that is a class. V is an object. It holds 1, 2, 3, kind of like an array, but it's an object. It knows how to respond to messages like, hey, what's your size? So you've secretly been using these things all along. Okay? Any questions up until this point? Are we ready for the private? For the example with private? All right. So let's get fancy. Let's do things right. And that will give us kind of like the best way to write the class. I'm going to teach you ways that people tend to write classes. Okay? The standard way of doing it. All right? So let's do it fancily. All right, so let us restrict access to our member variables. We do not like this. Point p dot x equals 42. We do not like this line right here. Because think about it. Say your point class only was for points in the first quadrant, right? Only for points in this quadrant of two-dimensional space. If you let the user have access to the x field, they can set the x field to whatever they want. They could set it to negative 42. And then suddenly, you're in one of these quadrants. If you restrict access to x, only allow users to change x in a way that works, that keeps it in the first quadrant, then your points are still correct. Does that make sense? We don't want the user to have access to our fields because then they could change them in ways that we don't want them to be changed. Right? So the secret is, instead of letting this happen, you need to give what's called, you just give a method, right? You give a method that's called a setter. Say p.setX and give 42 as an argument. This will be a method call, and that can set the x field only if it's the right kind of x. Like if the user tried to set it to negative 42, your method could fix that, right? And keep it positive or something. Whereas this line, it just sets the field. You can't really change anything about it. It's just like a variable access. If we force the user to go through methods to access the member variables, then we have finer grains of control over those things. Okay? That's beautiful. So let's restrict access. Let's say that our member variables are private, and you should always do that. Member variables should never be allowed to be changed like this. That is not good style, all right? So the second you restrict access to them, the user cannot do p.x anymore. You have to add public methods so that you can still get them and set them, all right? Those are called getters and setters. So if you want to get the x, now you need a get method. Get x, get y. If you want to set the x, set the y, you need a set method. So those are called getters and setters. Getters give back values, setters set the values. Usually they're of your private member variables, okay? And that lets you control the kinds of values that those variables can hold. That's beautiful. That's what we want, okay? So let's do it. So all these things up here are accessible to the user. We don't want these member variables to be accessible to the user. We're going to make a new section called private. And that's where these are going to go. Boop. So now, these cannot be accessed by the user. They're fine for us, the implementer of the class. They cannot be accessed by the user now. All right? So all these things are still accessible. These methods are still accessible. Okay? So the second I do this, I'm allowed to, in the implementation of the class, of course, talk about the x and the y. But in main, lots of red appears. I'm not allowed to have these lines anymore. Let me show you the errors that you see. It's like x is a private member of point. You're not allowed to touch it outside of the class. So I'm going to get compiler errors all over the place. The first one was like, all right, x is private within this context. Yeah. Y is private within this context. You're not allowed to talk about X and Y outside of the class. You see that? I'm restricting access. Information hiding. So if I want to use X and Y, I need to add getters and setters. Okay? I need to add these. I need to add my getters, and I need to add my setters. So a getter looks like this. It is going to be, well, just give back the value of X. So it's called getX or something. It takes no parameters, and it gives back the value of X, which is a double. Okay? Same for Y. And then setters, those are void methods because they just change the value. But they need to take the new X and the new Y that you want. Okay? So I don't know. They'll both take a double. That will become the X. That will become the Y. Does that make sense? So I'm making methods. I'm forcing the user to go through these methods to set the X and the Y. All right? So that's a getter and a setter. Is that what I want to do? Yeah. Okay. So let's implement these. Let's implement them in point.cpp, of course. So I don't know, below all these maybe. Again, this is points get y method, or points get x method. It's points get y method. Otherwise, it looks like a function. We don't want that. So these are really quick and easy to implement, assuming you don't want to check anything. But I encourage you to add little checks. See if you can change this after class to like force these or to only make points in the first quadrant. So get x just returns whatever x is, my x field. Get y returns whatever y is, my y field. Sorry, these are setters. This should be called set x and set y. There. So, I don't know, x becomes whatever d is. Y becomes whatever d is. This will set my fields. And you can imagine to have some complicated if statement inside to see like, okay, do I really want to set x to this value that these are passed along? Can I trust it? Is this what I want it to be? You have control now. You have control over all the values that your member variables hold. Okay? Any questions about this? These are your getters and setters. We've just restricted access to saying p.x. Now you have to say p.getx or p.setx to some value. All right, so back to the main file. Let's get this compiling now. So instead of setting p.x this way, I have to say p.setx to 42. You see that? Instead of saying p.y this way, I have to say p.sety to 43. That will correctly set them. Those are calling my setters. Okay? Then when I'm checking, hey, does p's x equal this? Does p's y equal this? Now I need to use the getters. Get x. Is that 42 now? Get y. Is that 43 now? Okay? Any questions about what I just did? Does that make sense? Just, okay, I can't do these lines anymore. I gotta do these lines. I have more control over my member variables this way. Oh my gosh. Set x, set y, and scale, and then use a getter again. Q.getx. That better be 5. Q.gety. That better be 7. Okay? I think that was everything. Yep, now it compiles again. And my test still passed. So those are getters and setters, also known as accessors. Getters or accessors are the same word. they access a value, and then mutators. So set x and set y, they change something, so they mutate the value. Okay. So that was quite nice. Access control. Go back. Just because of this privateness, now I'm forced to add these. And that's the right way to do it. All right, are we good to keep going? So that was the first thing. Next thing I want to talk about is, all right, there's something called const. I've already told you what const means in terms of variables. They're just things that can't be changed, or const parameters. Those values can't be changed if you use references. So I talked about const for parameters and just for variables as well. So if you have this function that takes a const string, inside the body of this function you can't touch s, right? You can't change it. It's a constant reference. There is an equivalent thing for classes. Of course you can take const parameters still, but there's an equivalent thing for when you don't want a method to touch its own member variables, any of them. So like you can make a method that you don't want to have touch, change, and by that I mean change, like x and y inside of this point, inside of a point object. That's what I'm about to teach you. You can still access them, just like this allows you to still access S. You just can't modify it. You just can't change it. And that helps you, the implementer, from doing accidentally something silly. So there's an equivalent thing when you don't want your method to touch any of its private member variables. What you do is you put const after the name of that method, right? That's all. It goes in a weird place. It goes after the name of the method, which is weird. And that makes it so that you are now confident your method does not touch its private member variables, or its member variables at all, even if some are public. That's what const does. So getters, for example, should always be const. A getter should not be ever allowed, right? It's supposed to give back a value. It should never be able to do something like this, like y equals 42, and then return y. No, we never want that, right? This should never be allowed. Okay, so with that in mind, let's add const to everything. So like double get x. What you do is you say const at the end of it. It's weird when you give a semicolon. And so this is called a const method. It's not allowed to modify its member variables. It's just allowed to look at them. All right? So let's do that for all of our getters. Boop. The setters can't be const, right? They're supposed to change our member variables. Can't get rid of it there. But this is how we can do this. Get x and get y const. And that means in the implementation, you also have to put const here in this weird place. They're const methods. And now this won't compile, which is beautiful. It's exactly what we wanted. Read-only object. So it marks the current object as read-only in the body. That's the technical terminology that it's using. And now it's not allowed. It won't even compile. Now I'm not allowed to change my member variables inside of my const methods. Sweet. And it all compiles and runs. Okay. Are there any other methods that could be const, that should be const? What else do we got? Setters can't be const. Getters are always const. What about negate, add, or scale? Should any of those be const methods? Should any of those not be allowed to modify their member variables? What do we think? The whole point of some of these, yeah, like negate, that modifies the x and the y. Does that make sense? Yeah. So this one can't be const because it has to change it. What about the other two? Scale, again, is kind of like negate. It needs to modify its member variables so that they're all multiplied by some value. But what about add? I claim that add is not, add is fine. Add could be const. Why? Yeah, you're just taking your current member variables, you're taking your x and y, right? You're giving back a new point. That's adding somebody else's x and y. Here's the implementation of add. Do I touch my x? Do I modify my x? I shouldn't have to, right? I'm just taking whatever my x is, whatever my y is, adding it to the other's x and y. And that's how I'm setting the result. Okay? That's how I'm initializing the result. This is not touching my current object, so this should totally be const. I shouldn't be accidentally modifying my member variables. This is just supposed to give back a new point using my values. So add should also be const. And again, it'll compile and it'll run because we didn't accidentally modify anything, right? But now we're guaranteed to never be able to. It'll be a compiler error. Okay? So, I think I'm ready to give you a question. Are there any questions before I move on to a question for you? This is definitely something to come back and study this. These are a lot of harder topics, I would say. Let's see here. First question. Here's a class, it's called blah. Please, as a group, you don't have to write it down anywhere, but just among yourselves, fix it according to all the guidelines that we talked about today, right? So class blah. Should some stuff be, I don't know, not public? Other things that we talked about. So yeah, take a couple minutes to look at this class definition, and you don't have to implement anything. Just see if you can change it according to the guidelines of what I said was a good idea. Okay? So take a couple minutes to modify that a little bit. Where would you add stuff? What would you change? And then I'll do it with you. All right. So this is like what the blah class should be like. It's like you make an object of type blah, you call it setter to 42, it should set the x member variable to 42. It should do exactly what we thought. But what's wrong right now? What should be changed? Yes, that's the first thing. Good. So x should be private, because otherwise I can be like b dot x equals 42. We don't like that. We do not like that. So this part should be private. And then there's one other thing that I thought about. What was it? Did we find it? One other thing that should be changed. Very good, yes. So this is a getter right here. It's just supposed to give back the value and not change the value. So this should be a const method. Okay, those are the two things that I mistakenly did, okay, or on purpose added here, okay? Any questions about why those should be exactly that? Better be a const getter, and all your member variables should always be private. You don't trust the user enough to set them directly. Okay, very good. So I have one last question, and then I'll, I guess, introduce your lab. I'll give you a few minutes for this one, maybe 3 maybe to think about it. But let's say we took everything we had, right? We have our point class, we take it all, and we add one more method called reset. It can't be const because it's going to change it. And the method is supposed to reset the entire point object to like hold zeros for x and y, okay? Something is horribly wrong right now with this reset method. See if you can figure out what it is. You don't have to write it down anywhere that is public, but among your group, see if you can like specify what in the world is wrong here. Why is this not a correct reset method? Why is it not going to reset my object to 0, 0? Okay, so take a few minutes to think about that. It's a very subtle problem, but it's in there. This is not going to work right now. All right. So, Let's talk about it. Did anybody notice it? Everybody see the problem? It's hard because I should probably like give you my code at the same time, which is not the easiest thing in the world to do. But did anybody notice the error? This is not going to do the right thing. Well, let's figure it out together then. So I'm going to add a reset method. How do I want to do this? Alright, let's do it here. Boop. This is from the pushed ice. Let's call it reset. Void reset. Can't be const. There. And let's implement it. Let's implement it in exactly the way we have down here. It's points reset method. That's all correct. And then this is how it's setting x and y. Dun, dun, dun. And of course, when I copy from PowerPoint, it ruins all the spaces. So just give me a second. Are you done? Okay, good. Better. So there's the method. Let's make a test for it. I don't know. Why not? I claim it's not going to pass, so let's just see how badly it does. Test. I guess we'll call it test reset, right? So let's just be like q.reset. The method takes no parameters. And then, I mean, x and y should be 0, right? Reset. I need to actually call that. That would help. And it fails. Oh man, reset's not doing the right thing. So, all right. Here is the implementation. Let's, I guess, let's output. What in the world are the x and the y's then if they weren't 0, 0 after I reset? The problem should be visible on the screen right now. See if you can see it. See out q.getx, and then like a space or something, I don't know. q.getY. So here I'll output them as well. Ooh, there's still 2.5 and 3.5. They didn't change at all. Does anybody see the issue here? Look at the setters above. What's the difference? The setters correctly set the member variables. What is the one difference in terms of syntax in the current version of the reset method? This is setting x properly. It's just saying x equals d. How's this one setting x? Double x equals something. This double is the problem. What does it mean when I say double something equals something? Like if I just said that in main, what did it do? It makes a variable. This is making a variable called x, which is different than my member variable, also called x. I am shadowing it. Remember that word? So let's talk about it. This will bite you. I've seen this bite my 41 students so many times. So try to ingrain this in your memory and never do this, but we're all going to do it. I do it too. So we were in main. Main called test reset. Test reset. Test reset made a q that had an x and a y, right? That held 2.5 and 3.5. Yes? And then we called the reset method. All right? We call the reset method. We're up here, we're inside of the reset method's implementation. And when we're inside, right, the names x and y become our member variables x and y. So if I were to say x and y, I'd get these guys correctly. But watch what happens. When I say double x equals 0, I just made a brand new local variable to this method. It's just like a function. It's all the same, just like it would have been anywhere else. Doesn't matter that it's inside of a class. This makes a brand new variable called x. It shadows the other x, the x that you wanted to change. This makes a brand new variable called y. It shadows my member variable called y. They're local variables to the reset method. And so when reset returns, you're back down in test reset, and q's x and q's y never changed, even though you said q.reset. At the very start, the x and the y were those. You could have modified them, but you just shadowed them by making new variables. That's what we did. Does that make sense? Do we see the problem now? It's very subtle. Very important to see them. All right? So, oh gosh, how do I want to do this? So I don't know. The following code creates new local variables. They're called x and y. They shadow the x and y member variables. So sad. Okay? We don't want that. So how should it have been said? Just like the setter, right? This is what we should have done. We should have said x equals 0.0. It's a member variable. It already exists. Y equals 0.0. That is going to work. So now there's 0, 0, and we passed our test. Okay? So yeah. If things aren't changing the way you want them to change inside of a method, come back to this idea. Maybe you accidentally added a type, and you made a variable when you should have just modified a member variable that already existed. Okay? Any questions about that? That's a fun one. Fun little subtle issue. Okay. If we're good with that, that is all the slides that I want to do today. Next time we'll come back and remember that counter example that I gave at the very start of class, and then the counter function library that we made before? We'll do that next time. I'll actually do it in full in the way that I want it to be done. So that is what we look forward to next time. And then, yeah, the only thing I want to do today after this is release your next lab, Lab 5. This will be a 2-week lab, so do week 10. This one is not about classes just yet. It'll be about functions. And it's about rational numbers. Okay? Rational numbers. So let's talk about it. So first of all, rational number, if you've never heard that phrase before, that's just a fancy word that means fraction. So we're going to make programs that represent fractions. Something like a over b, where a and b are both integers. Okay, integer fractions. All right? So we are going to make a library that works with fractions, so like adds them and multiplies them in the way that we knew how to from math class. We also want to keep our rational numbers simplified, right? You'd rather work with 1 over 2 rather than 4 over 8 because they're the same fraction. We always want to simplify our fractions, okay? So we're going to worry about that. And then we're also going to implement multiplication of 2 rational numbers. That's super easy. Just multiply their numerators with their denominators, right? And addition is the harder one since you have to find a common denominator. So we'll save addition for later. We're going to come back to rational numbers with classes in a future lab. So, okay, let's go to the starter code for Lab 05, and I'll try and talk about it. Let's see here. Yeah, I'll just go to it up here. It's not a big deal. Do I have it on my... Cool. All right, that works. And this is Lab 5. So here are the 4 files that you'll have. And so we got libraries and things. Okay, so what you're going to do is you're going to make a rational number library in rational.cpp. Okay? Oh, sorry, it's rationals.cpp. Excuse me. That's a typo there. So let's look first at rationals.h. Here's our library. Here are the 3 functions that are in the library. So the first one that I'll talk about is like simplification. You give a rational number as a numerator and a denominator, right? It's supposed to represent numerator over denominator. And this function will simplify it. You're taking those numerators and denominators by reference so that you can change it to make it the smaller form, right? That's what rational simplify should do. And then pretty string just takes your fraction, simplifies it, converts it to a string so that you can print it later with like a slash in between or something cool like that. And then multiplication, it looks like this. It's a very long function. It takes the first fraction that you want to multiply, right? Numer 1 and denom 1. You want to multiply 4 over 8 or something by 5 over 12. Then you take the second fraction, numerator 2, denominator 2. And then you have to give back a fraction, but that's 2 things, so you could use structs, or you could just take 2 reference parameters. So the result is going to go in result numer, or the numerator of the result will go there, and then the denominator of the result will go in result denom. That's how you return 2 things. You just modify those values as a reference. Okay? So that is the library that you will make. Any questions about that? So you're going to be representing functions. I think I have, where do I have something about that? It might be, let me quickly thumb through my notes. I don't know, let's put it here. Your lab. Boop, boop. So, yeah, the idea is you have a rational number. The numer is going to be 2, and the denom is going to be 4 to represent 2 over 4, something like that. Okay. Let's see. Simplify in times. They don't return anything, but they modify their reference parameters. Okay, because of call by reference. And rational pretty string returns a string. Returns the string form of the rational number. It doesn't print anything out in this function. It gives back a string that could be printed out later. Okay? So don't do any printing in rational pretty string. That is incorrect. Of course, I lost my start menu. Okay, so give back a string. Don't print anything out. And yeah, I've made a cute little sample program that will help you test your solution. You'll compile it with your library, of course. And here's what the output should look like. You can enter in 2 fractions and it will simplify the first one, multiply the second one, and all that stuff. Okay? So let's go to sample program.cpp. So using the header file, you know all the things that you can do now. So here you can enter a fraction. You can call simplify on it, which should change numer 1 into denom 1. Then create a pretty string of it, and we'll print it out. And then we'll do the same pretty printing with the second fraction. Okay, and then we're going to multiply using rational times fraction 1 with fraction 2, whatever you typed, and the result is going to need 2 ints, right? A numerator and a denominator. And so we'll pass those along as reference parameters, and they'll get changed, and we'll print out the result just like that. So that's using the library. Does the use make sense? Does the library make enough sense? What you're taking and what you're returning? Because really, I have a lot of confidence that you can implement most of these very easily, except for simplification. That one takes some fancy stuff, okay? So let's talk about that. So let's go to rationals.h again. Rational simplify is going to get a little weird. Here's rationals.cpp. There's a whole lot more comments there that I want you to read. But here is rational simplify. There are a lot of steps to simplify a fraction because think about what needs to happen, right? I have this fraction. I'd like to simplify it. What do I need to divide by, right, on both sides to make it 1/2? That's the simplified form. So I better divide by 2. Yeah? How do you get the 2? Because it could have been 4/8, and again, now you need 4. You need to divide by 4 if it's 4/8, right? How do you figure out what to divide by? The answer is the greatest common divisor. So I've implemented the greatest common divisor function for you. It takes two numbers and gives you back their greatest common divisor. That's how you simplify a fraction. You divide by the GCD. Because the GCD of your numerator and denominator is this. GCD of 2 and 4. This would return to you 2. That's the value you want to divide by. You see that? So you're going to use the GCD function that I made for you in your implementation. So use this inside of simplify. Also, for simplification, you have to worry about some stuff as well. So like if it's negative, so if it's like 4 over negative 8, that's also ugly. Like you shouldn't simplify it. First of all, GCD only accepts positive things, so you're going to have to get rid of the negative for a second. You need to make this negative 1 over 2. So you need to like bring the negative up as well. That's the correct way to simplify a fraction. The negative should always be on top. So you need to follow my instructions here to implement it. So first you need to figure out if the rational number is negative or positive. And there's a few cases because negative 1 over negative 2, that's a positive fraction, right? So you need to remember that. You need to keep track of all that. So there's going to be a few if statements to check and see if it's negative. Save that in like a Boolean variable for later. And then convert numerator and denom to positive numbers because GCD only accepts positive numbers. You'll negate something later when you need to. And then you simplify it using the GCD. And then you should negate the numerator if the answer should be negative. Okay? That's going to be your implementation. And again, you don't have to return anything. It's a void function. It just modifies numerator and denom because they're passed by reference. So does simplify make a little bit more sense now? There's a lot of steps, but just follow them. It'll all make sense. Okay? So that's simplify. Times, that one should be pretty easy. How do you multiply two fractions? It's just, I don't know. You're multiplying a over b by c over d. The answer is ac over bd, right? Then I think I might want you to simplify that, but you can just call your function for that. That's not too hard. Yeah, simplify after performing your operation by calling rational simplify. You took care to implement it up here. You can just call that from now on. That's quite nice. So that's times. And then finally, pretty string. And this is the kind of pretty string you should be making. Okay? So if your numer is 2, for example, and your denom is negative 44, that's really supposed to represent the fraction negative 1 over 22, right? That's the correct simplified form. So you need to simplify your fraction and then make a beautiful string that looks like this. You say negative 1, then a space, then a slash, then a space, then the denominator, 22. Okay? So that's the kind of string you're going to return. So build up a string like that. Okay? That's the idea. So if numerator was 2 and denom was 4, you'd make that 1/2, and then the string that you give back is 1 space slash space the 2. So you have to work on converting numbers to strings as well. Okay? There is a nice toString function for that. It'll take a number and give you back a string. Okay? So toString, if you call that, it's a library function on 42, it'll give you back the string 42. And then you can just add that to a space and a slash and a space, and then the other denominator. Okay? So that's the kind of cute string that I want you to build. And so, yeah, the sample program should look like this if you give these exact values. And after you've got all that working, then I've made a fancier test file for you that, again, you need to compile with the library. Okay? So this is in the test file. There's another main function there. and this will have a few functions that are test functions. So test simplify makes a fraction, simplifies it, makes sure that the simplification was done correctly. Same for times, it multiplies some stuff, make sure that multiplication was correct. And then pretty string, it just checks to make sure it's being simplified, it's exactly the right kind of string, all that cool stuff. So yeah, those are the functions that I have made. Those are the tests that you will get passing. And then it is a 2-week lab, so I also want you to write your own tests. Okay? I want you to write 2 more tests in this same style. So make another function, make 2 more functions, and each function should call assert true once. So I want to see you call assert true twice more somehow. Those will be your tests. Okay? They can be about anything. Maybe combine some of these. Like, all right, multiply something and then pretty string it. Something like that. But yeah, use my tests as a guide. You'll be writing 2 more of your own tests. Okay? Each should call assert true just once. So that is the last thing. Okay? You'll be writing your own test after you get mine passing. Any questions about any of that? Because that, I think, is all. So you're going to modify the implementation file for the library, and then also you're going to write some tests. So you're going to turn in both of those files, rationals.cpp and test.cpp. All right? And that, I think, is everything. I think I can stop recording now.